Right, this is a review of homework 13. So the first question said 75 people were asked to indicate their favorite ice cream flavor, vanilla, chocolate, or strawberry. Data appears in the table below. I'll show you that in just a minute. And then perform the appropriate chi-square test for goodness of fit to determine if there is a preference for a particular flavor. In doing so, show all the intermediate calculations, including the expected frequencies and the contribution to chi-square for each category, determine the appropriate critical value and sketch the comparison distribution, and then provide a short interpretation of the results. So here is the table. So we've got 75 people, and these are the observed frequencies. That is the number of people that said, I prefer vanilla, I prefer chocolate, I prefer strawberry. So here's our chi-square statistic. What you can see is that the statistic is looking at the difference between the observed frequencies and what was expected. Okay, so the first thing we have to do is we have to figure out, under the null hypothesis, what are the expected frequencies in each category. In other words, what are the expected frequencies in each cell of the table. Okay, and then once that's determined, once we've got observed and expected, we can just use the formula to determine the chi-square. Okay, so these are the observed frequencies. The way that we figure the expected frequency is that under the null hypothesis, there is no preference between the three flavors. Another way of saying that is that there is an equal distribution across the categories of this variable. Okay, so this is an equal distribution. So what does an equal distribution look like? Well, it just means the same number, okay, the same frequency in each one of the cells in the table or across each of the levels of this categorical variable. So we just determine that by taking the sample size, 75, and dividing by 3. So there we are. So we've got our expected frequency is 25 for each. So if there's no preference between vanilla, chocolate, or strawberry, we expect an equal number of people to prefer each one. Right? So now that we have that, we can use our chi-square statistic, and we can look at observed minus expected. We're going to square that and then divide by the expected. Oops, my animations are a little bit off here. Okay. So what you'll see is that basically for each cell in the design, we're going to perform the calculations where we've got observed minus expected squared and then divided by expected. And then we're going to repeat that. So here's the numbers for vanilla. We're going to repeat that for chocolate and repeat that for strawberry. Okay, so doing 10 minus 25 gives negative 15 squared. 225 divided by 25 is 9. Okay, so the contribution to chi-square for this cell is 9. The contribution for chocolate is 25, and the contribution for strawberry is 4. So summing that together, adding it all up, gives a chi-square of 38. And I like to point out that you can kind of look at the contribution from each cell in the table to the overall chi-square. So you see that of the 38, 25 points, I guess for lack of a better word, comes from this cell. And you can see that's because many more people preferred chocolate than expected under the null. Okay, so we get fewer people preferring vanilla and fewer people preferring strawberry, but the big departure from the null is in this cell, and that you can see that because of how big this number is relative to the other two. So this is the cell that is really having that big contribution to chi-square. Now, of course, that's a really big number, but we always have to evaluate our statistics relative to a critical value. Okay, so we're going to determine a critical value. Our comparison distribution when doing null hypothesis significance testing for a chi-square is a chi-square distribution. A chi-square distribution, you can think of it as if we were to do this little experiment over and over and over again under the null hypothesis, we're going to expect that there's exactly equal preference, we'd get a chi-square of 0. But we know just due to sampling error, we're not going to get a chi-square that is perfectly 0, but we want to know how big could our chi-square get for us to still say, there's still sampling error, versus no, the chi-square that we calculated is far too big to be due to merely sampling error, and therefore the null hypothesis can't be true. We have to reject it. So the way that we determine that is with our chi-square distribution. Degrees of freedom is determined by the number of categories minus 1. Because we had 3 categories, vanilla, chocolate, strawberry, we've got 3 minus 1 is 2 degrees of freedom. Animations are a little bit screwed up, that's fine. So here's our chi-square significance table. What you can see is we just look up our degrees of freedom in this left-hand column. We're going to use significance level 0.05, which is your default unless otherwise specified. Always use this 0.05. And then we've got a critical value of 5.992. And with a chi-square, there's no such thing as directional tests. Okay, so that you don't have to worry about a positive or negative. The values are always going to be positive. So there's our sketch. This is our sampling distribution of the chi-square statistic. This is our cutoff value. Okay, so everything to the left, we're saying this can still happen. All of this can happen if the null is true. Okay, all of these chi-squares can technically happen if the null is true, but all of the chi-square values to the left of this line, to the left of 5.992, happen 95% of the time. The values here happen less than 5% of the time. And so it's the chi-square values that are over 5.992 that are unlikely to happen if the null is true. So this is our region of significance, that if we landed here, we're going to say that we've got a statistically significant result. Clearly, a chi-square of 38 falls in that region of significance. It's higher than the critical value. So what can we say? We can say that preference for ice cream flavor is not equally distributed across those levels of the categorical variable. So in other words, people do have a preference which seems to be for chocolate over the other flavors. Why? Because we expected 25 people to prefer chocolate, but 50 did. We preferred 25 people to prefer vanilla and strawberry, but only 10 and 15 did respectively. So more people seem to prefer chocolate than expected, and fewer prefer strawberry and vanilla than expected. However, there's a way to do follow-up tests to be able to say, is there actually a stronger preference than expected for chocolate versus strawberry, or for chocolate versus vanilla, or we could even compare vanilla versus strawberry if you wanted. So it's possible to do a follow-up test, which you do by just calculating another chi-square, but you only use 2 cells from the table, just the 2 different levels that you want to directly compare. Okay, and then you just need to change your critical value accordingly. And if you're doing multiple of these follow-up tests, you want to adjust your alpha level using a Bonferroni correction. So I don't show that here, but I did give examples in the lecture, and you should refer to that if you have questions about how to do a follow-up test. Here's a second question. The data below are from 100 newlyweds that were tracked over 4 years. At the end of the 4th year, the researchers determined which couples had children. So yes or no. Okay, yes, these couples did have children, and no, these couples did not. And then which couples stayed together. Okay, so they stayed married, or they separated, currently separated, or they divorced. Perform the appropriate chi-square test to determine if there is a relationship between having children and marriage outcomes. So the appropriate chi-square test in this case is a chi-square test for independence. Okay, so in this question, carry out the steps of hypothesis testing, sketch the distribution, and then determine the effect size. So the first thing is to state a research question as a research hypothesis and a null hypothesis about populations. So here's the null hypothesis. And by the way, I didn't go through all the steps of hypothesis testing for problem 1, but that's also something that I show you in the notes and is also presented in the chapter. But this should give you a sense of those 5 steps, because for the goodness of fit, as well as for the chi-square test of independence, it's very similar. So our null hypothesis is that marriage outcomes are independent from having children. Okay, so that's always the null hypothesis in the chi-square test for independence, is that the 2 variables are independent of one another. What does it mean to be independent? It means that there's no relationship between the variables. So we can say that there's no relationship between having children and marriage outcomes. But the alternative hypothesis is that marriage outcomes are dependent on having children. In other words, we would say that there is a relationship between having children and marriage outcomes. So think of a chi-square test for independence as kind of similar to a correlation. A correlation is a correlation coefficient, or a Pearson correlation coefficient, as we've learned in other lectures, is a statistic that can be calculated to determine the relationship between two continuous variables, where the values of the variable are measured along a continuum. Here, with chi-square, we're also trying to detect if there's a relationship between two variables, but those two variables are not measured using a continuous scale of measurement. Their values don't fall along a continuum from high to low with these intermediate values in between. Rather, a categorical variable or a nominal variable, they're synonyms, the values are categories. Okay, so as in have children versus don't have children. Those are two categories, and you have to be at one or either level with no intermediate values in between. Same thing with marriage outcomes: married, separated, divorced. It's a categorical variable. The values are categories. You can't have any values in between any two adjacent values. Okay, so a chi-square is just to determine whether there's a relationship. A chi-square test for independence is to determine whether there is a relationship between two categorical variables. So the second step is to determine the characteristics of the comparison distribution. Comparison distribution, of course, is going to be a chi-square distribution. The way that we figure out the shape of the chi-square distribution when doing a chi-square test for independence, that is two variables, is we have to determine degrees of freedom based on the number of columns and the number of rows that are in the contingency table. So where's our contingency table is right here. Okay, so in our contingency table, we've got 2 rows and we've got 3 columns. So the way that we figure out degrees of freedom is to take the number of columns minus 1, okay, which was 3, so married, separated, divorced, and then the number of rows, have children, yes or no. Okay, so columns minus 1 gives us 2, rows minus 1 gives us 1. Multiply those together, gives us a degrees of freedom of 2. Here, for whatever reason, I said you should use the alpha level of 0.01. This is just to keep you on your toes a little bit. We see these tables that have different alpha levels. By default, psychology and other social behavioral sciences use 0.05, but it is absolutely possible, depending on the test and the aims of the research, to use a more lenient critical level. Okay, this is like an easier critical level to surpass versus a more stringent one. So in this case, we used a more stringent one. You can see here that the critical value is higher. So this is going to be a tougher critical value to surpass. If you think about our sampling distribution, that line, rather than being at 5.992, is moved out to 9.21. So that's a critical value that we're going to use in this case. All right. Fourth thing we're going to do is to determine the sample score on the comparison distribution. Just like doing a chi-square test for goodness of fit, we first have to determine our expected frequencies. So the way that the expected frequencies are determined for each one of our 6 cells is we have to take the row total divided by the total number of participants. And then once we've got the row divided by the total, we're going to multiply that by the column total. And that will give us the, that process or that formula will give us the expected frequency for each cell. So I didn't do all 6 calculations, but I gave you 4 to get a sense of where the numbers are coming from. So to get the expected frequency for the number of people that should be here that had children but that stayed married, is we see that there was 66 couples that had kids, there was 34 that didn't, okay, so 100 total. So what we want to know is, and then what we also see is that there's 39 people that stayed married, there's 16 that separated, and there's 45 that divorced. So what we want to be able to figure out is we want to say, okay, look, there's 66% of people that have kids. There's 34% of these couples that don't have kids. So we want to know what is that breakdown among the 39 couples that stayed married. Essentially, we're asking, what is 66% of 39? That's going to give us our number here. And what is 34% of 39? That's going to give us our expected frequency here. Okay. And so the way to get there is to take 66 over 100 gives you 66% or 0.66, and then multiply 39 by 0.66, and that yields 25.74. Okay, so that's this calculation right here. What about married but no? 34, okay, so the row total divided by 100 times 39. So basically we're saying 0.34 or 34% of 39. So essentially what we're trying to say is, okay, there was actually 19 people that stayed married that had kids, and there was 20 people that stayed married that didn't have kids. However, based on the overall numbers, the overall percentages of people that have kids versus not, we expect 66% and 34%. Okay, so that's what we just determined. A good check on your math is to add up your observed, right? So your observed 19 plus 20 should equal 39, but then add up your expected. So 25.74 and 13.26 should also equal 39. And so that's a really good check on your math to make sure that you've done it correctly. And you can see here, if you add it up, 0.74 and 0.26 gives us a 1, okay? So 1 and 5 is 6. Plus 3 is 9, and then 1 and 3 is 9, right? So that adds up to 39. Follow the same process or the same logic for separated and divorced. Essentially what we're saying here is show me 66% and 34% of 16. Show me 66% and 34% of 45. Okay, so these are the calculations that support those numbers. Once we have our expected frequencies, what we're then going to do is it's the exact same formula. We're going to go through the kind of the component calculation. So the first thing I did just to organize my work and split it up is to say we know that one part of the formula is to get observed minus expected. So that's what I've got here. Okay, so 19 minus 25.74 gives us negative 6.74. 20 minus 13.26 gives us 6.74. Okay, 11 minus 10.56 gives us 0.44. So these are all of our calculations. So you basically got to just repeat the same operations, the same calculations for all 6 cells in the design. Okay. Now the next thing that we have to do is we take that number that we previously had, we square that number, and then we divide by the expected. So that's what we've got here in these cells. So 1.76, what I did is I took that negative 6.74, I squared that number, and then I divided by 25.74. That's how I got the 1.76. I repeated that operation for all 6 cells in the design. And what we have here, what you can see is that the numbers in these cells represent the contribution to chi-square. Because what we do is we sum up each of these cells, okay, and we get the overall chi-square. So 1.76 plus 0.02 plus 1.34, et cetera, plus 2.59 yields a chi-square of 9.18. Okay, and so you can check your math. You should be right around this ballpark. If you're off by just a little bit, like a 100th or 0.05 or even a tenth, you probably did it right. But take a look at my numbers and see where you're at. Again, I'd really like to look at the contribution to the chi-square because this gives me a sense of where do the observed frequencies depart from the expected. So with our contribution to chi-square for our separated folks, you can see that these are really small numbers. So there's not much of a contribution to chi-square at all. And if we go back to the data here, we can see that there's a very small difference between what was observed and what was expected. Okay, so that you're not going to get a contribution to chi-square in that case. Okay. However, we can see that the biggest number here, we've got a 3.43 for married that don't have kids. You can see that that's because we would expect under the null hypothesis only 13.26 couples to remain married without kids, but 20 did. So this is a big departure. And just to interpret it right away, we can say that there are more couples that don't have kids than stay married under the null hypothesis of independence between these two variables. Okay. So decide whether to reject the null. So our chi-square is 9.18. This is less than our critical value of 9.22. So we fail to reject the null. So based on these data, there's insufficient evidence to suggest that there is a relationship between having kids, between having kids and marriage outcomes. Now, what you should, of course, notice is that if we had used an alpha of 0.05, we would have said that there's a relationship. Okay, because the critical value there is only 5.992, in which case we would have exceeded a critical value of 5.992 associated with an alpha 0.05. So the other thing that I wanted to illustrate is just if you set a more stringent critical value based on an alpha of 0.01, essentially what we're saying there is we need to see a sample result that happens less than 1% of the time due to sampling error, if the null is true. So that's a more stringent example. Okay, so here's our sketch. So we can see, I didn't quite think, that line should be like almost right there, but you can see that we just didn't quite fall in the critical region. So we fail to reject the null because it was awfully darn close, but strictly speaking, our test statistic is less than the critical value, and whenever that happens, we fail to reject the null. Okay. We can still calculate an effect size to get a sense of, the size of the relationship. The way that we do that with a chi-square test for independence is to calculate a Kramer's phi. This is done by taking our chi-square and then dividing that by n, which is the sample size, 100, and then dividing by degrees of freedom from the smaller side of the contingency table. So our contingency table was 2 rows by 3 columns. So the smaller side is the rows. There's 2. Degrees of freedom from the smaller side is 1. Okay. So we just take the square root of 9.18 divided by 100 gives us the square root of 0.0918, which is equal to 0.3. We can interpret that effect size as being a medium effect. So here's our conventions for our Kramer's phi. Smaller side of the contingency table was 1. So that's a medium-sized relationship. Okay. So we can say that, there appears to be a medium association there, but based on an alpha level of 0.01, we would be forced to say that is a non-significant relationship. If we use an alpha level of 0.05, we would say that there is a statistically significant relationship there. If we desired to have a statistically significant result, and we still wanted to use the 0.01 because we wanted to be that much confident in our result, we would have to get a bigger sample size. So a sample size of 150 or 200 would likely give us enough power, assuming, of course, we have this medium effect to detect a statistically significant result at that 0.01 level. Okay, so that's an overview of both the chi-square test for goodness of fit and a chi-square test for independence. Some review of the calculations on the homework assignment, as well as some general review of the logic of both tests and an overview of applying the steps of hypothesis testing.